My name is Alan Campos, and my
Peter
partner is,
Gallup.
we're with California State Polytechnic University, Pomona. Our advisor is Professor Herder, and we are the IoT solar tracking charger. This is just our table of contents. If you would like to see it, and we'll pause for a bit. Next slide. Our objectives. To make a solar power system as efficient as possible, to explore the possibilities with an IoT system, for the IoT system to send us data regarding the battery status. Okay, so let's explain what solar power is first through this summary. The use of the photovoltaic effect has been used since 1954, and it was discovered by Bell Laboratories. How a photovoltaic cell works is by having an N-type phosphorus doped silicon layer and a P-type boron doped silicon layer. An electrical field is created by this PN junction, and then when light hits this junction, it creates a flow of current. Once cells are put into a modules or an arrays, they can create vast amounts of energy or power, as only one single cell can create up to 2 watts with direct sunlight and about 0.8 watts at 40% sunlight around there. And then the benefits of solar power are, of course, sustainability, renewable. It's a renewable energy, can be its own system away from the main infrastructure. And by this, I mean that in a lot of solar systems, a lot of it is connected back to the grid, but you don't have to do that. It can be its own standalone system working independently. And it is low maintenance for the most part. What is IoT and what are its benefits? IoT, or the Internet of Things, is a network of physical items or appliances that are able to communicate with one another using networks and the internet. They can exchange data and talk with one another in order to work remotely and possible autonomously. The benefits and our goals for using IoT in this project is for a system to be more independent. With IoT, we will be able to get notifications and data regarding the charging of the battery without us having to check it constantly. With this technology, we hope to be able to expand it on it by having other systems attached to the solar power generator. And by this, I mean that since we're already using an IoT system, we hope that later on we'll be able to connect more information so that it can be sent to us, since the IoT system is already implemented.
Okay, so now we're going to talk a little bit about the parts that we're using for our particular system. So this is the argon particle board, and it's the main controller board that we're going to be using for our project. And so the main pins that we're going to be using on the left side there are going to be the ADC channels. So the first four ADC channels, ADC 0 through ADC 3, are what we're using to convert the analog voltage values from the LDRs to the digital values that can be compared and worked on from within the system. So then, and then we also use one more ADC actually for the IoT signaling system, which is going to be explained further later in the presentation. And then, so on the right, we have the PWM outputs that we're using. So we're going to be using pins 7 and 8 there, which are the PWMs for the motors. And yeah, the only other pin that we're going to be using on the right side is the V-bus output, which provides 5 volts to power the motors. And this pin is only active if we are able to have the micro USB connected. So that's the reason that we aren't able to make this system actually wireless. But it is possible to, if we could make the motors work with a 3.3 volts on which is a pin from the left side, we can actually obtain that from a single cell LiPo which would be input to the 3.7 LiPo on the right side that you see. So anyways, you can see here we have the power schematic for the argon, which basically shows how we obtain the different voltages that we're using, or well, we're only using the 5 volts, which would be at the very top via the BUSB outputs at that point. And so here you can see the microcontroller overall schematic. And so you can see it's using an NRFS 2840 quad flat pack microcontroller, which basically has, you can see on the lower left-hand corner, has the V-bus connection, which is the important one that we're using for our 5 volts, which is probably the most important connection that we have for the system here. And then on the left side, or no, on the right side, sorry, you can see that we have our antenna system set up. Or this is the setup that they have internally for the antenna to work properly. And it's not a very complicated system. It only requires a system of capacitors to process the Wi-Fi signal properly. And then moving on to the motors.
For this project, we use servo motors because they're able to work on 5 volts and they can be quite precise. They use a PWM signal that is already provided by the particle, and we simply have to connect the motors to the particle and code it so that they would move depending on the status of the LDRs. Some of the additional electronic components are the 4 light-dependent resistors, 4 68 kilo ohm resistors, 1 mini breadboard, 1 2.4 gigahertz particle antenna, 1 solar panel, 1 LiPo battery charging module, 1 LiPo battery, the 16850 charging holder, and the 16850 LiPo battery. Additional mechanical components. We used a copper pipe for the Y-axle, 4 rectangular wood segments, or the legs for our platform, a panel platform with cardboard underneath, 4 plastic cup segments, 1 base platform rotating, 1 base box, 4 furniture sliders, and 1 outer motor housing. So the cost for this is around $65 is what we spent producing this project, which is extremely cost effective for anyone who's trying to do solar system tracking, especially if they're trying to implement IoT. I believe that it is one of the most cost effective things that can be done.
Especially with the Argon board, it seems to be the most cost effective for an IoT system that we could find.
So this is the hardware block diagram. As you can see, the sun is going to go directly to the LDRs, which are going to be sensing and comparing the amount of sunlight that they're getting, which is in turn going to go into the particle board. And it's going to tell the particle board to move the servos in whatever way, depending on how the LDRs are reacting to the sunlight. Additionally, sunlight is going to be hitting our solar panel, which in turn is going to go back to the particle board, and it's also going to go to the battery charging module, which is going to charge the actual battery. So this is our solar tracking system overview. The LDRs are mounted to the corners of the panel platform. Each is connected to a BDR circuit to divide voltage between the LDR and a resistor, which is a middle point, and it equals the variable voltage for ADC. Analog to digital conversion used to obtain voltage across LDRs. Digital voltages are compared and necessary adjustments are made using pulse width modulation. So this is our solar tracking code. And in this part of the code, it's basically taking the average of the LDRs and it's getting the difference between like the top and the bottom and the right and the left when the sun is actually hitting them. And then continuing the solar tracking code in here, this is so that it can actually, since the servos move 180 degrees, we have it so that the servo on the y-axis or the right and the left is able to move 4 degrees at a time, and then our y-axis, the up and down, is moving 1 degree for better precision, or is what we're trying to achieve for it.
also to avoid excessive amounts of torque from moving too many degrees at once. And so here we have the light tracking demo video, which is our best representation of the system working the way that it's intended. So as you can see, it's not entirely responsive to the light, to the LED light that we're using, which is a relatively powerful light. Yeah, we probably could have gotten better results if we were actually using the sun, but today we happen to have an overcast day that doesn't really allow for that. So as you can see, it is actually tracking in the left and right direction, however, pretty consistently. So yeah, I try to move the light closer, but it doesn't seem to have much of an effect. So I think the main issue is just being able to generate enough of a voltage change based on the light that we're using. Seems to be a limiting factor to our ability to demonstrate how it functions. So yeah, moving on. So to the next slide, we have the lithium ion charging module, which is using the TP4056 IC chip, and it activates at a range of 4.5 to 5.5, which is well within the range of voltage produced by the solar panel that we're using. So we have the B plus and minus outputs going directly to the battery, to the LiPo battery, and then we have out plus going straight to the argon. And so this is going to provide our IoT signaling. So when we get that out plus signal, that's what tells the argon to send the Wi-Fi signal or to publish the events, which I'll explain later. And then we have out minus going to ground. All right, so an overview of the IoT system is that it uses the publish command to publish an event to the particle website via the Wi-Fi signal that it connects to. And so this event is going to be recognized by an applet, which is created using the IFTTT app, which is the if this then that app. So it just takes an event and performs an action based on that. And in this case, it's a notification to a cell phone. And so, yeah, the notification that we set up is, it just says solar tracking charger message, the battery is done charging. That's all that we were able to create for that. So this is the program. It's very simple. After you assign the input pin and the variable name to the pin that's activating the IoT signal, then you define the pin mode as an input. And once that's done, you just take an analog read of that pin. And if it's above a certain amount, in this case, 3000 seems to be the amount that's prevents too many signals being sent, and also being able to detect when the signal is being sent properly. And so all it does is it publishes the battery status being done, and after that it delays for 500 milliseconds in order to prevent another signal being sent too quickly. So we just want to have like a steady stream of signals, not constant signaling to the IoT system. And so here we have the IoT demo video showing how that works, because we're not actually going to be able to show that system working because we're not going to be able to charge a battery from so yeah, you can hear that it was able to receive the notification properly, and it's difficult to see there, but it says solar tracking charger message, the battery's done charging. And so that's essentially how the system works with the IoT. And it would work just the same if we had a battery connected in there that was fully charged and the system received the signal from the charging module.
So these are the mechanical details. The mechanical properties of this design includes a base with an x-axis motor, or the motor that's moving left and right, attached to it. The base will hold a tower that will house the particle board and support the additional base for the solar panel that is mounted on. On this tower, the y-axis is controlled by an additional motor or second motor that is connected to our copper axle, which in turn is connected to the base holding the solar panel. Torque was one of the most important aspects to account for since they provided our desired movement, and that is why we went with the MS-18 microserver, which is able to provide most of the torque that we required for it. Um, uh, the holding torque was also a really important factor since it needed to hold out a lot of the weight once the, the solar tracker is aiming like towards the sun, like up towards the sun. It should be able to hold its position when needed. So these are our preliminary designs, and we don't have a lot going on here. We did start off by trying to use an Arduino R3 board, but after doing more research, we found that the particle was able to provide everything that we needed for this system to do. So these are our final design images. As you can see, we're using the particle board. It is connected to a breadboard, and then the top breadboard is connected to the LDRs, which is in turn connected to the bottom breadboard, which is connected to the particle board, and that's how everything is able to communicate with one another.
Okay, so the final design pros that we have, or positive aspects of design, are that mainly is that it's cost effective and it was relatively easy to build, and also so we used hot glue for the main adhesive of the system to put everything together, keep it all together, which allows it to be very easy to deconstruct. So you just can reheat that hot glue and just about take it apart just the way that you put it together. And so yeah, we did have to do that a few times. So that's essentially why our system does look a little bit, I would say, unrefined, but ultimately it performs the job that we want it to. So that's good. And so then the next one that we have is the Argon. The Argon board is very compact and it performs all the necessary functions. And we couldn't have asked for a better system or more effective system in this particular case. So, and then the next we have we used long wires for most of the just about any signaling wire because we knew that we were going to have to it was going to have a variable length in order to allow for the full range of motion in both directions. And so, and this also allows the wires to be easier to route ultimately because we can more easily move them to whatever position we need them to be in. And lastly, we use long wires for the base motor. So that allows it to rotate through its full 180-degree range of motion without disconnecting. And some negative aspects of the design are that the IoT signal is takes a little bit of time to be recognized by the IFTTT app, which is based on the strength of the Wi-Fi signal. So it can take upwards of like 5 to 10 minutes. But yeah, in the demonstration you saw, it can be very quickly also. It can be recognized very quickly also. So yeah, it changes. But anyways, yeah, the biggest issue that we were dealing with is that too much weight being on the ND axle, just not allowing the rotor to, or allowing the motor to produce the torque that it needs in order to move and hold that entire axle in the position that it needs to be in. And this could have also been related to the fact that the LDRs were not isolated effectively by the plastic cup segments that we're using currently. Yeah, we were experimenting with using like different types of PVC pipe and things like that would isolate them better, but yeah, those don't seem to do a whole lot of extra work besides what the systems that we already are using. So moving on, we have the issue with having long wires is this. It does make the wiring a lot more messy and much more difficult to troubleshoot. As you saw in the our final design, the wiring is kind of difficult to follow. So yeah, trying to make sure that all those connections are properly connected is kind of a chore. And then the last one is kind of obvious. The hot glue that we used is going to melt in the sun, which is going to cause structural weakness. So, you know, this type of system would definitely need something that's a heat-resistant type of adhesive, or ideally some sort of metal that's definitely not going to melt at all in the situation we want it to be in.
But this is completely possible to do if we were able to 3D print or get better materials, like my partner said. But that does increase the cost of the system. And while we wanted to keep it as low budget as possible, as cost effective, we also wanted to make it as light as possible. So that is why we used hot glue and other like lighter materials like wood. And then that's another reason why we stuck with the cups instead of like heavier PVC pipes, which would just add more weight to that overall system.
Yep. All right, so then I believe this is our last slide. These are the potential improvements that we saw that could be made for our system. And definitely the first one is going to be a lighter and smaller panel platform that allows it to move more freely. And a more effective method of isolating the LDRs so that we can maximize the amount of voltage change that we get between light and no light conditions. Another important one could be to use bearings on the sections that, for the legs sections that the pipe needs to rotate inside of. So that would allow for the rotation to basically be frictionless and much more stable, for sure. So then ultimately, if we were to create this design for some type of actual company, we would want to create a unique PCB that basically utilizes all the same aspects as the argon, just in a much more compact and dedicated type of form. All right, so then also another thing we could add is more IoT notifications that would tell the user when the battery has begun charging and perhaps when it has reached half charge, which would require some kind of an additional ADC measurement of across the battery to find out when it reaches its half charge point. And another one is to have shorter wires for connecting LDRs to the BDRs, because those wires really didn't need to be as long as we made them. We just didn't know from the start of how long those wires were going to be based on the mounting of where that PCB was going to be. So those ended up being longer than they needed to be. And lastly, we definitely need to utilize better routing techniques that allow for the wires to be out of the way of all the moving parts, so that there's no restriction to anything that's trying to move, which is a problem that we faced a lot also. We had to do a lot of rerouting of those wires in order to get it to function properly. And so lastly, you can see here a list of references. These are the major references that we were able to get very important information from, such as the information about IFTTT and just the basics of how a system like this works based on how the LDRs need to be positioned and things like that. Okay, so now we're going to move on to our somewhat live demo, in which we're going to turn the system on, and my partner Alan is going to.
I will use that camera.
Okay. Okay, so you can see there the light is flashing, meaning that it is currently searching for a Wi-Fi network to connect to. Get a whole shot here. All right, so now it is connected and is currently functioning. As you can see, you can probably hear the motors trying to function, trying to activate, but it seems that they don't have either enough power or they're not reading enough voltage change across the LDRs in order to activate properly. But as you did see in the previous demo video that it is able to respond to a light like this. So yeah, we're kind of frustrated with the fact that it doesn't seem to be responding consistently. And so now to demonstrate one possible reason behind it not functioning, we're going to measure the voltages across each LDR, like between lit and non-lit conditions, to see just what type of voltage changes we're dealing with, and seeing the system should be able to detect these voltage changes. So just a second here. So we've got it on a millivolt scale. And I'm going to go ahead and, oh, like that, okay. Okay. So that should be the lit condition. And now, Alan, if you can move the light away, or yep. And that's going to be the non-lit condition. Oops. And so you can see there's a significant change. It's almost seems to be, it's not very consistent, but less than 1 millivolt for non-lit. And then with lit, I believe it was about 7 or 8 millivolts. Is that right? Yeah.
Yep.
And so that's about what we get across each LDR for non-lit and lit conditions, which we would think the system would recognize and be able to make an adjustment based on those. But yeah, it doesn't seem to be as responsive as we would like it to be.
And that is going to conclude our presentation. Thank you for joining us and listening. And I hope you learned something at least and found interest in it.
Yeah, thank you. And we appreciate you viewing our presentation.